okay, like what are you supposed to look for? Just every atom connected to the same things? Or like how do you know?
Yeah, are you talking about, let me scroll down here. Like here, for example.
Yeah, like yeah, so is all you're looking for the fact that like all of those like hydrogens on the right are connected to one carbon? Like is that what you look at? Or I don't know, that just like wasn't clear necessarily.
Yeah, so when we're looking at, you're basically looking at the structure as a whole and then making a decision about, I was just trying to see if there's more kind of pictures that I could try to show you, but I guess this might be the best one for now. Or like, this is another good example, right? Um, but let's just look at this first example. Where did it go? Right here. So when you're looking at, remember that this down here, let me see, let me just change my color. So this down here, that's very thick. Let me just erase this so I can feel a little better. Okay, so this portion down here, and as always, forgive the messy writings and everything, but and then this is just the rest of the right. But so if we take a look at each of these hydrogen here, these are all one away from this carbon, and these are all two away from this carbon, right? So it's connected to one directly and one kind of like indirectly, so to speak, right? And the same thing is true for these here. It's connected directly to a carbon that is connected directly to a carbon. And we could say the same thing, obviously, about these, right? And so that's what makes these three CHs magnetically equivalent, because they all have the same structure, so to speak, right? So the hydrogens are connected directly to a carbon, which is bonded directly to a carbon, right? So there's nothing that's different between any of these. Versus, and then we've got, now I'll draw the rest of my structure, right? I'll ignore my squiggly line. Okay, so now I'll draw the rest of my structure. Versus now we have an O, and then we have another C, H3. Versus these hydrogen are bonded directly to a carbon, which is bonded directly to an oxygen. So that's why this one would be different and more de-shielded than this one over here. And then, obviously, you've also got this that kind of tells you have 9 hydrogen here. To look on the scale. If it's 10, it's hydrogen. If it's, I think, 200, it's carbon, right?
Yeah, and I just had a question. So,
Yeah.
when you're reading yeah, I just want to make sure. So the length of the peak, like
Yeah.
how long it is that I thought somewhere in the video, if I remember correctly, she said that it's not the number of atoms you have. Does it have to do with like I don't know if it has to do with like the strength of the bond or like I just get confused between like the peak being long versus the peak being along the scale, like what each is attributed to.
Sure. Yeah. Yeah. So, you can see here, this is 3 hydrogen and this is 5, and the 5 is shorter, right? And let's see, here we have, oh, this is a carbon scale, always, I'm saying this, I know Dr. Pillai and Dr. Austin say this all the time, but just always double check your scale before you start doing anything. So I just want to reiterate that. Let me see. And in this one, we have, this is more about splitting. So see, this is 3 peaks, this is 1 peak, and this is 1, 2, 3, 4 peaks, right? So that's what this one's more about. This is about this splitting situation. So let me see. I'm trying to remember because maybe it was the splitting one. So the more the further along the scale this way, and as you can see here, right, it's the more de-shielded it is. So that means that these here,
Yeah,
these
like,
here are more de-shielded than these over here, right? So
yeah.
that's why it's further along this way. The peaks, I believe, see, I had a biochemistry exam, so I didn't review every single little material like I usually do. So I apologize.
You're taking a class too while you do this?
Oh yeah, yeah. I have a couple. I'm working for a couple different professors, and I'm taking biochemistry, and um, yeah,
Well,
yeah.
wait, and don't you work too?
Well, I work for the professors, and then I work for Dr. Pillai, and I work for Dr. Holacek, and I volunteer at the Phoenix Children's Hospital and the Red Cross.
I don't know how you have any time. But
I don't.
anyway,
I don't, to be honest. Anyway, so okay, so there's a difference between these, right, versus like these is like the strength of your right strong vibration is these like deep versus a weak vibration. Are these kind of more shallow? See what I'm
okay,
saying?
so the length has to do with the strength of the bond, I think.
So it has to do with the vibrational strength, which is right here. So if you have stronger bonds, you will have an increase in frequency, which means a frequency is this way, right?
Or the
Um,
lighter atoms thing.
yes, exactly. So, or you have decrease in atomic mass is also an increase in frequency. So,
But yeah,
yeah, go ahead.
what we don't go where, oh, that page that you're
This
on right
page.
there. Yes.
Hmm.
On that same page, um, I don't know, I just have like a problem with that. Like I just like forget this a lot. Um,
You're funny.
so no, yeah. But the thing is, like, okay, for the bond dissociation energy part, I just like don't know, like, intuitively, like, why it makes sense. Like I just get confused because, like, in the first chapter when um like the strength of the bonds were normalized, and then it was like you basically have to like put in enough energy to get to that threshold. But then in the chapter 2, it was kind of reversed in that you plotted your peaks or like your curves, and they weren't normalized. And
Mm.
then, so like I just get confused with the bond dissociation energy. Like when it's a really strong bond, I would think that like you would have to put in a lot of energy to break it. So I got confused with like that trend. And I didn't know if you can like explain it to me because I just don't understand.
Yeah, let me see. I had made a graph. I probably have since erased it, but so these two are, I basically combined this graph here and this graph here to help me understand. I would write these on my exams to help me understand like bond association. So I would do, right, and I would have, I guess technically I should have 4 up here, but anyway.
Yeah, so
Yep.
yeah, I just I just get confused with this because I know intuitively, like SP3, I don't know, this is the way I do it. Like SP3 is the highest energy. And so
Mm,
essentially, like it's very easy for the electrons to escape the grasp of the nucleus.
I get what you're saying. Yeah. Okay. Yep. The highest energy.
Electrons.
Yeah. Yeah. Yeah.
And so therefore the bond dissociation energy should be low, I think, right? Because you don't need to
Mhm.
put in a lot of energy. Is that
Yeah. Yep. That's correct. Yeah. Yeah. So if this is your normalized line, your SP3 has smaller bond association energy than would your SP. See that there? Um, right. And then, so this is, so you notice the difference with radicals because then the radicals, it really depends on what kind of radical you're getting out. So, got to remember that when you're looking at a graph like this, you have your reactants on this side and your products on this side. And so if your products are all the same, then that's where you can get this relative energy. Versus when your reactants are all the same. You see what I'm saying? So that's the difference here. So here our reactants are all the same, but our products are different. And that's why we're getting all these different, we have a third degree, a second degree, a first degree radical.
yeah, so can you go yeah, don't scroll away from that yeah. Yeah, that one you're on the bottom. This is the one I get confused about because
This
for
one here.
example, yes, because for example, I thought that the professor said that a third degree radical is the most stable, right? And if it's the most stable, the molecule is like the most comfortable in that state. Like it doesn't want to dissociate essentially because it's in a good configuration. And so to me, I would think that you would have to put in a lot of energy in order to like break the stability. But yet on the graph, the most stable structure has the smallest bond dissociation energy. So I think of it in reverse and I don't know why that is.
Okay, I understand what you're saying. I'm trying to think about how I can explain this to you so that it makes sense. So, yeah, so our tertiary is our most stable because it has what you could consider to be like the equivalent of resonance, right? But not really. It just has a lot of friends around it, right? So it's more
Yeah.
stable than the lone radical. Um, so decreasing energy of non-bonding electrons.
Oh,
So,
maybe that's why. Maybe that's why. Because so you see, this is my problem. You can think of it in two different ways. You can think
yeah,
of it in the way I think of it, like it's most stable, so it takes the most amount of energy to like get it out of that comfort zone. Or you can think of it like it's the most stable, so it's the lowest in energy, and therefore it also takes the lowest amount of energy to like break. But like, aren't they
yes.
both true?
Well, so I think you're mixing up most stable, so it doesn't want to move. This you got to remember that this is a radical at the end of the day. So radicals ultimately always want to be in a bond, in a pair. So like here, up here we have the most stable is SP because it has the most bonds to it. And so that makes it the most stable. It makes it the strongest, right? Versus like here, our radical is stable, but it has low energy, like low non-bonding energy. So like bond dissociation energy. So you're trying to dissociate a bond, but this has low bond energy, period. Whoops.
Yeah, yeah,
So
that's
yeah, I think when it's like, I think you're mixing up the two concepts about like, yes, with resonance, if you have more resonance and it's more stable, then it doesn't want to um, dissociate, so to speak. But this is not a bond. This isn't bonded. That's the point. It's a radical.
yeah, that's yeah, I think I overlooked that point. That's a good way to, like good thing you said that. Like it's a good way to remember it that way. Like that don't, yeah, I think I was looking at it like it was a bond. Because I think if you look at it like a bond, then that I don't know. I shouldn't even say that because I'm confused. So maybe my technique is flawed. Honestly, it probably
No, it's
is.
okay. You figure it out as you go. Yeah, but I would think about it more of like it has lower energy. Like it's non-bonding electron. The single electron here has the lowest energy out of all of them,
Yeah,
making it
no, that's
the
good.
most stable, right? And so because it has low energy, it doesn't take very much to dissociate that that radical. Because remember, the radical that we're looking at, right? We're like talking about dissociating this. So this is most stable here, which makes this have a low energy. So it doesn't take as much versus this is the least stable and it doesn't want to dissociate because this is the least stable. This one's the least stable, so it does not want to dissociate. Bond dissociation, right? We're talking about dissociating this bond. Where is it? We're talking about dissociating, right? This bond here.
Hmm.
So we're talking about dissociating that. So because this is the least stable, this is going to have the highest bond dissociation energy because it
Hmm.
does not want to be stable. Whereas this bad boy is like, hey, you know what? I don't really want to be, but like, but I'm chilling, because I'm more stable with all my friends around.
Hmm.
Does
Yeah,
that
so
help?
a bond dissociation energy is energy input into the system,
Yeah,
right?
it's energy. Yeah, it's how much energy you have to put to dissociate, break that bond.
Got it. Okay.
Yeah.
Um,
So
also,
back to
sorry.
IR. Yeah, yeah, go ahead. I
No,
just want
sorry,
to
go
share that.
ahead.
No, no, you're fine. Um, I wanted to find that because you were asking about that in particular, but forgot what you had asked last time about. So this just means that there's like a lot of it versus a little of it, right? So that's what this is like the um absorbency right here, absorbency scale. So that's like how much the more the deeper these crevices are, the more there is. Um,
Wait, the
but
more there what? Wait, sorry, what it was the word?
no, that was just saying the more there is of that. So, like for example, if you just have this one, right, CH here, right? This, oh, I'm sorry, the more strength it has.
Yes, and therefore, yeah, the more strength in the bond, the more vibrational frequency the bond experiences. I guess they go hand in hand,
Yeah, yeah,
I think.
yeah, yeah. So here, and these are like you had said, these are some of the ways that you can kind of, and then this vibrational frequency, this is dependent on whatever this is, right? Like whatever the bonds are, not whatever this is, as if I don't know, right? But like whatever the bonds are, whether it's like triple bonds, bigger molecules, smaller molecules, single bonds, triple bonds, all of that type of stuff. So that's what you'll notice. Something that I always did on my exams is I would typically they'll draw a line on 1500 for you anyway because we ignore it. But I also drew one on 3000 because you would have your I believe CH2s to the right of it and CH3s to the, I'm sorry, CH2s to the left of it and CH3s to the right of it. I wrote it correctly. I just said it wrong. So that was a good way for me to start when it came to like trying to read these.
And wait,
Um,
on
yeah,
that same page,
yeah.
yeah, so okay, so is the CH bond, so it says the CH bond has the highest bond dissociation energy, right? So then we're saying that that one's the least stable. And that like confused me only because well, okay, see, this is my problem. I don't know how to like look at it. Like there's different ways to look at it, right? Like you can say
Yeah, conceptually, you mean?
as yeah, you can say like a carbon carbon bond, the single bond, there's no difference in electronegativity, right? So there's no dipole.
Yeah,
And then
exactly.
so then that's one way to look at it, and you can be like it's the most stable because it's like nonpolar, kind of like it's a nonpolar bond. But then
And we're
you
supposed to consider that with C and H as well.
Yeah. But
Yeah.
like then the thing with the C and the H is that like isn't also one of the things you're supposed to think about the fact that like hydrogen is a really small atom, so its nucleus can get really close to carbon,
The
and then
tighter
like that,
bond.
yeah, and then like doesn't that make it more like stable? But like apparently not based on the bond dissociation
No,
energy.
no, no, no. That it's a good point. So look, me. We just have to do this every so often. Okay, so we've got a carbon and whatever. Let's say we have a carbon, right? Unequal carbons. You know what I mean? Okay. Then we have a carbon. We have a hydrogen. And let's say that these lie on the same axis. So let me zoom in so it's a little bit easier to see here. So we have, let's just say 1, and then we have 1 plus x. Let's assume this is x, right? So a carbon bond is equal to 1 plus x. A carbon hydrogen bond is just equal to 1. So when we're talking about bond dissociation energy, it is higher bond dissociation energy because it takes more energy to break this bond here versus this bond here. This bond, gosh, this bond is bigger by X amount, so it's less stable because it's further apart, right?
Mhm. I think my definition of stability is wrong.
Okay, what's your define stability or stable? Let's
Well,
decide.
I mean just like when I'm saying the CH bond, I say okay, like the nuclei can get close together, therefore it's like very stable and it's like low in energy, right? But
Yeah.
the thing is,
If it's
it's
low in energy, listen, you're on the right track. If it's low in energy versus this is a little higher in energy and we're trying to just break them off, who's got to go further?
no, yeah, but that's the thing. That's how the graph was in the first chapter, but you know the one we just looked at with the
Yeah.
radicals? And then we were like, the most stable radical had the lowest bond dissociation energy. You see how it's like opposite?
Yes. I will say that radicals will screw you up if you um because they are a little backwards. Just remember that this is a whole bond. You are splitting, for example, in this, you are splitting an atom from an atom, and they're each kind of getting their own there's no radicals involved. I don't know how else to say this. Just there's no radicals involved. So it's more intuitive.
Mhm.
Radicals make you think radically, right? You have to think on a radical kind of asinine new level where like things are a little bit backwards. So if it's more stable, if the radical is more stable, it takes less energy to break it because it's capable of living on its own. Think
Yes.
about a kid who is pretty stable and works a job and goes to school and all these things. Like it's pretty easy for them to want to leave the house because they're like, all right, like I've got a good support system, I've got money in the bank, whatever, versus a kid who's never worked a day in their life, has zero education, no life skills at all. To get them to like leave the house and live on their own, that type of person is extremely unstable. So it's going to take a lot. It's probably going to take like an eviction notice and a police force to get them out. Do you see what I'm saying?
That's an amazing analogy.
So, maybe think about radicals like that.
Yeah, okay.
Radicals demand radical thinking. So
Yeah. No, yeah, okay. That's yeah, no, that I will not forget that. Okay.
okay. Cool. So, but we don't really have to worry about radicals here. So we learn about radicals a little bit there just so that you have the idea and you've seen it. But I want to say we really don't touch on radicals a whole ton throughout the session. So, it generally speaking, it's probably behind you. I'm not saying it might not pop up here or there, but you won't have to, worry too much about the details. A lot of this stuff is like, we're skimming the surface, and there's a lot of stuff that I don't even know because it's goes into way greater depth than what this course will ever call for. So,
Yeah, no,
um,
I hear you.
yeah,
On the spectroscopy topic also,
yeah, yeah.
can you explain? I don't know if this was anywhere like explicitly in the notes, but I thought that the professor had made a comment when she was describing one of the bonds to say like the peak should look really sharp. So I
Oh,
didn't
yeah.
know, like, yeah, like why a peak is sharp or it's not, or how you know.
You know, it's literally that's the thing about this chapter. And I'm looking over my own notes right now just to
Because they didn't really give an explanation for why. They kind of just said it is, and then I didn't know if like it would make it easier to identify certain ones. I don't know.
yeah, so when you're going over the videos in the spectroscopy thing section, there is excuse me, weaker I'm trying to see large dipole. Do you remember which part? You don't remember probably. Um because
Um,
there's a lot of like little nuances, right? About like, the like wide troughs, the broad troughs, um, versus like a couple spikes on it, or like how many peaks it has versus, because I know that there's some like the aldehyde and the ketones are usually kind of like that sharp, single, like all the way down, it comes all, pretty far down the page, and it
yeah.
doesn't really like branch too much. So there's a few of them like that will do that. But I know a lot of the times it has to do with like the double bonds, or um I'm trying to look at this compared to some of my notes here so I can try to explain. But you said you don't remember which part she was talking about, correct?
think I mean it was in the 1.2, I believe, the real absorption bands when she was going through every single combination. But
Yeah. Yeah. There's a lot of them on there too. Um, yeah. So,
it could have been the aldehyde because that looks really sharp. I'm not sure exactly. Oh no,
yeah,
no, I found it. I wrote an annotation. It was the NH bond. She made a point of saying that it's really sharp for some reason. And I think that could be due to the hydrogen bonding, but
what page is it?
oh, it's six
Oh,
of
six. I passed it.
1.2.
Yep. Yeah, I'm looking at mine. Weaker hydrogen bonding, sharp NH peak. Oh, I wrote it too. That's so funny. Um, let me see. The OH bond, let me see, amine NH stretching vibrations are also broad due to the hydrogen bonding, but NH hydrogen bonding is weaker than OH. Nitrogen is less electronegative, and some non-hydrogen bonding NH vibrations can observe small, sharp peaks or spikes on top of the broad absorption. The NH bond dipole is also somewhat smaller than the OH bond dipole, and NH absorptions tend to be somewhat weaker, and so that's why you're not seeing the deep troughs, so to speak, or the low peaks. There's usually two small non-hydrogen bonding peaks for a primary, and one small peak for a secondary, because you have two versus one hydrogen. A tertiary has no NH bonds and no signals are observed. In this case, IR peaks are assigned to individual bonds first and functional groups second. So the broad peaks are first assigned to vibrations of NH bonds, from which we deduce that there must be an amine functional group. Yes. And so amines are typically in the 22. Is that what it is? Oh, they're over. Is this one the one she was talking about over here? Oh, okay. Broad with spikes. Yeah. So this one at the bottom of page 6, you see the two spikes for the two different hydrogens. So that makes it a primary amine.
Yeah. I guess I just don't truly know what the spikes mean, maybe because like I don't know, there's just a lot going on there, like different lengths, they're different along the axis for like frequency, and then like they have different bond strengths, but I don't know. I I mean, wait, actually, so I don't know. If you're not sure about that one, can you go to page 2 and like maybe
Yeah.
like I don't, because like even on page 2,
The yeah, go ahead.
she
I'm listening.
circles the CH bond and then says that it's weak. The bond is weak, or the way that I understood it. She says there it is a weak vibration, and vibration is directly correlated with the bond strength. So I guess it's a weak bond relatively. Then she circles the C double bond O and says vibration
Ketone.
strong, which makes sense given that that's a stronger bond.
Yep.
But then the C double bond O is like further to the right on the axis, but I thought that the axis is increasing vibration to the left. So I'm
It
like
is.
confused.
Mm-hmm. Yeah, so you're increasing, so these spectrums are backwards from what you would what your scales would normally be, right? So larger vibrational frequencies are on your left. So with a C double bond O, you're dealing with both. Let me see right here. You're dealing with both a double bond and you're dealing with higher electronegativity, the smaller lighter atoms, higher frequency. So you have your double bond will be increased slightly, right? So we even on the CC we have it around 1600, and here I think the C double bond O is what? It's like 18 or something. Let me look. Yeah, so it's in the 2000s, yeah. Usually strong, yeah. Ketones, yeah, you're in like you're above a 1700, right? And then oh my gosh, it's right here. Let me see this. Yeah. So, you see like it's somewhat comparative, right? So C double bond O, or rather C double bond C and C double bond O, they're kind of in that same region, right?
So the presence of a dipole is more important. I guess this is like what I'm trying to get at. I
Mm,
think that the presence of a dipole, which is present in the C double bond O due to the electronegative oxygen, has more of an influence on the vibration than the fact that it is a stronger bond than CH. Because if you look on page 3, it says bonds that are strong have higher vibrational frequencies, but that's not what we see on page 2 because C double bond O is stronger, but it has a lower frequency. So then, do we conclude that the presence of the dipole trumps that?
yeah, and you have to remember too that those um let me see, let me look at this. Yeah, so your double bond region, you see your triple bond region is between your double bond and your single bond. But those have to do with decreasing. Let me see. Because your SP2, because a lot of it has to do also, some of it has to do with your hybridization, which will also change with your bonding. And so for example, your SP2 hybridized are going to be to the left of, so it's going to be like higher, like see over here, you've got, these are your SP3, SP2, SP for your carbons. Here's your aldehyde. Where's your ketone? Here's your ketone. There's an ester, right? So far, so good.
Mhm.
Aromatic or benzene ring.
So I guess the fact that the hydrogen bonding is the furthest to the left, because the hydrogen bonding is just a special type of dipole, right? So I guess we can think of it like the dipole trumps the like presence of a double bond or a triple. That was what wasn't clear to me in the video.
There is, I thought she had literally talked about this somewhere. Oh man.
Because she made a big point of saying, like, you must have a dipole moment, you must have a dipole moment for there to be the IR radiation interacting with the bond. So, like, I thought that was really important. But then when she went over to, like, what are the frequencies that bonds vibrate, and she talks about bond strength and the mass, she doesn't talk about the presence of dipoles anywhere. So then I was like, does it, like, I don't know. I guess I'm just gonna go with that.
Okay, so
And
the width
say,
of a peak represents the range of wave numbers over which a particular vibrational mode absorbs infrared radiation. This width can provide valuable information about the molecular environment, like hydrogen bonding and concentration or purity of the sample. Stronger bonds, like double bonds, exhibit sharper peaks compared to weaker, more flexible bonds. So that would be what she was talking about with the nitrogen, probably the nitrogen to hydrogen, because it's a stronger bond with the nitrogen, because it's more electronegative than carbon. And then complex molecules can show broader peaks due to the presence of numerous slightly different vibrational states. The number of peaks provides information about the different functional groups and complexity of the molecule. Simple molecules have fewer bonds. Symmetry and chemical environment, different types of carbon hydrogen bonds, sp3, sp2, or sp hybridized carbons. Um, the
wait, sorry,
y-axis,
which
go
one
ahead.
was the one about the length? Can you just repeat that one more time? Versus
Um,
the sharpness?
number of peaks. Oh, about the length.
Yeah.
About the sharp. Is that what you're talking about?
Yeah,
Well, that
like
doesn't
if
really.
it's long or if it's sharp. Like I
No,
didn't get the
she didn't say
distinction.
long. She didn't say long. She says it exhibits sharper peaks compared to
Okay.
weaker ones. Stronger bonds exhibit sharper peaks. So
Hmm.
your double bond, triple bond, they will have sharper peaks than your single bond. The y-axis typically represents the absorbency of transmittance in the IR. Um, so transmittance is it measures the amount of light that passes through the sample. So more light that passes through, the more transmittance there is. So it is usually expressed as a percentage. Higher transmission values indicate that more light is passing through, with lower values showing greater absorbency. It indicates the intensity of absorption and mainly depends on concentration of sample and bond dipole moment. So higher bond dipole moment has greater absorption. I just want to make sure I was reading that correctly. And then the x-axis typically represents the wave number, which is a measure of the number of wave cycles per unit distance. The wave number is usually expressed in units of reciprocal centimeters, 1/cm, It is inversely proportional to the wavelength, so higher wave numbers correspond with shorter wavelengths and higher energy vibration. Wave number scale allows for identification of specific functional groups and molecular bonds based on their characteristic absorption frequencies. So this scale here, that's why she also gives you this, so that way you don't have to like memorize all this. So this scale here, our wave number is inversely proportional to the wavelength. So higher wave numbers over here have shorter wavelengths.
Wait, are
So
you
these,
drawing right now?
oh yeah, do you not see it?
No.
Oh, there. Do you see it now?
Oh yeah, I see it now.
Oh, okay. I wasn't drawing too much. I was just,
Oh,
um,
okay.
yeah, I wasn't really doing anything much. So, and higher energy vibration. So this has higher energy, shorter wavelength. Based on their characteristic absorption. Okay. And then this one, which we already know, this has to do with how much light. So more light. No, more light indicates the intensity of absorption. Higher transmittance values indicate, yeah, more light. Okay.
There's just a lot of things to pay attention to, I guess. Like,
Yeah. Yep. I would definitely agree with you on that one. Let me see. Conjugated single bond. I want
because there's
to
also
help this make sense for you. Yeah, go ahead. What'd you say?
I was gonna say, to your point, you also brought up the hybridization. I actually forgot about that one. Like, there's like, you can either look at the hybridization, you can look at the bond strength, like single, double, or triple, and you can also look at whether there's a dipole present. And like, all of those different factors, like, I guess, contribute to where it's placed on the scale. And there's no like clear place that says what trumps what. Although I think the dipole trumps the bond, but then I don't know where hybridization falls into that. I really am not sure.
So one other thing that she had mentioned was, let me find it. So in general, we can use this as a guideline. Electronegativity, pi electrons, so double, triple, right? Hybridization. This is not an end all be all rule, by the way.
Mhm.
Hydrogen bonding and solvent effects, which oh wait, this is for deshielding. Never mind. Sorry. Just kidding. This is for the next concept. Ignore that. That's the next concept. Yeah. I would say when it comes to understanding what you're looking at, there are some just general rules to know, which is like being able to interpret this graph here that I have on the thing. Like some of the biggest things to kind of like understand is like however many spikes you have here will determine the degree to which like this amide, right? Like will determine the degree to which your amine is, right? Your 3000 line, all your little troughs just to the left of it will be your sp2, and just to the right of it will be your sp3. um your triple bonds are gonna lay typically in this area. Those are major things to look out for when you're interpreting a graph. That's why I said, like, the most important, there's a lot kind of to this, but if you can really understand this graph, for the most part, you're gonna be doing pretty well. I'm trying to bring up, this is alkenes. Let me see, where are we? Deshielding IRs, interpreting IRs. So let me just add this and we can go over it, right? Let me just open this up. Oh, good. Let's see how long it'll take, right? Whoops.
I don't mean to interrupt.
No, you're fine. Go ahead.
So yeah, I was just looking over all of the different combinations because I don't think that I'm solid on it yet.
Yeah, tell
Um,
me.
and it says on page 5 on the bottom example, it says um the SP hybrid one bond
Mhm.
with H. Bonds vibrate with frequencies around 3300. And then it says they are distinguished from OH and NH bonds
Mhm.
because they are sharp. But I I thought that it's the OH and the NH that are sharp, right? It's not the CH.
So it just, the sharpness has to do with I want to make sure. Oh, there we go. Stronger bonds exhibit sharper peaks compared to weaker bonds. So yeah, so let me see. SP, carbon SP, hydrogen bonds. So that means that it's that's your hybridization. So it's a stronger bond because the hybridization has, remember your SP, SP2, SP3, right? So when you have SP hybridized, your bonds are going to be stronger because they're more like you have all your electrons in them, versus SP3, they're kind of all they're in that tetrahedral
Yeah.
shape, right?
Yeah.
So
Yeah,
this
I
is where
know
I
how
think
to
the hybridization comes in. Yeah, go ahead.
yeah. No, I know how to like compare SP to 2 to 3. I just didn't know. I mean, maybe I'm just like getting into the weeds completely. I don't know. I just don't want to like overlook something because I honestly find reading these graphs to be rather challenging and
Mm.
understanding what they are saying. I just like I didn't know how to compare an SPCH bond with like an OH. I don't know. I just thought that a hydrogen bonding, or I guess actually no, I shouldn't call that hydrogen bonding because it's only one bond. It's not between molecules. But I don't know. I just thought that the OH would be a stronger bond. But again, I think I'm getting this wrong because I'm trying to compare
So on the
two
next
things that
page,
aren't compatible.
so on the next page, so there's stronger dipoles, right? So your OH has a stronger dipole than NH than CH, right? So it says on here, bonds to more electronegative atoms are or elements are stronger and should vibrate with higher frequencies. NH and OH also have large dipole moments. Their IR absorption peaks should be strong. for example, one OH has an absorption strength that is equivalent to that of many CH bonds. So that's why, like, for example, if you're looking at this one on page 6, how you have your CH3s, it's a pretty long, right? But because you have a lot of them, you have a lot of these hydrogen, these hydrogen carbon sp3 hybridized bonding, sp3 carbon hydrogen bonding, right? And so that's why you have, but like compared to this one OH bond, like it's almost the same, right? Not quite, but I'm exaggerating a bit, but you get what I'm saying, you know.
Mhm.
Um, so
And
that
then,
that
oh,
dipole makes it stronger. Yeah, go ahead.
sorry.
No, you're
No,
fine.
I was just gonna say like, wait, so then, yeah, so then the statement on the previous page, on page 5, I guess I'm just reading it wrong, because it says CH bonds vibrate with this frequency, and then they are distinguished from OH and NH because they are sharp. So I guess I read that and I thought they was a CH bond, but I guess they is a, maybe that was just,
No,
I don't know.
no, 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 you're right. Like they are distinguished as in the CSP hydrogen bonds are distinguished from OH and NH bonds because they are sharp. So
So
you'll
the
notice,
CH is sharp.
yeah, yeah, the CH is sharp versus if you look over here, the OH, they're broad. See how it's a
Oh, yeah,
wide,
yeah, yeah.
broad.
Oh, but I thought that the sharpness was like which one is a stronger bond. I thought it OH bond is stronger.
It is stronger, but that's why it has the broader, because it has strong, larger dipole moment. So it has that broader peak
All
versus like
right.
a CH bond doesn't have much of a dipole moment. So it's just kind of like it's there and it's gone, you know?
Okay. Okay. I think I see. Okay.
Yeah. And then the next one down is the nitrogen, and it has a broad peak just like before. See, initially up top, it's broad. So that's how we know it's, nitrogen or oxygen or something. But we can distinguish it from the oxygen because there's two spikes on it, meaning that there's, the two hydrogen bonding, right? So we know it's one first degree, um, primary amine, excuse me. Um, yeah, so that's how you can, hopefully distinguish a bit about like the oxygen, hydrogen, or alcohol versus like an amine, right? As you might see like a little bit of peak on it, but still overall a broad peak.
Mm-hmm. Okay.
Um, yeah, and then on the next one, you've got your CH bonds and your sp2 bonds and your alcohol. I mean, your ketones, excuse me, is to the right of it.
Okay. So then, yeah, then the presence of the double bond, that's in the kind of middle region. Okay.
Yep, yep.
And then the other one was, oh yes, the triple bond. It is, oh, they talk, okay, you have to look at the fact that it has a large dipole and I guess it's a strong bond from the triple bond. So strong absorption. Okay. Okay. And then, okay. Um, I had a question also that I made a note of on page 8, if you don't mind.
Yeah, I'm on there.
Um, so when the professor had done the C triple bonded C and then single bond H, like it's the last example, the last thing she had written.
Yep.
And then she had circled the C bonded with the H and then drew an arrow to the leftmost peak.
Yep. Yep.
And I didn't understand why the CH was like, I mean, it's at like 3,300. Like, why is that so high? Isn't that supposed to be like It's like almost a non-polar bond and doesn't have like that much of a dipole or electronegativity or
This goes back to the hybridization, just the SP.
oh.
That's what that one's about. That one just strictly has to do carbon-carbon triple bond absorptions tend to be weaker. The bond has a very small dipole and only usually observed for the asymmetrical terminal alkynes. So,
Mm,
you know,
okay.
your terminal alkyne, right? So like at the very end,
Mm-hmm. Okay,
typically a lot of your alkynes are going to be like in the middle, right? But
okay. I just can't forget about the hybridization. Oh my gosh. Okay,
yeah,
good thing
no,
this
it's all
is
good.
Saturday.
You'll do fine. You'll be fine, honestly. It's not like horrible, right? So if we look at this on this, let's just look at this, right? Example that I have up, just so we can kind of, so we have, you know, sp2, sp2, right? And then this is an sp3, and this is an sp3, sp3, right? With our hydrogens. These are my hydrogens. I just draw lines, which I think you know. But anyway, right? And so I would always draw my line right here on the 3000. These are my sp2, and these are my sp3. Did I get that backwards? No, I have no, it's the other way around. No, that's right. That's right. sp2 and then sp3. Um, right? Versus this is specifically, I think, just we're looking at hybridization, right? So we have an H here. This is sp. There's nothing going on here. sp3, sp3, sp3. Same, 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 same. 1, 2, 1, 1, 1, 2. Okay. I'm not gonna write out all the SPs because I think you can figure that out by now. But if you can't, I will write them down. But I don't want to insult your intelligence. Okay, so if we're looking at this graph, where would you say? Let's start on the right side. Where would you say that this molecule here might land?
Okay, we're looking at the carbon-carbon double bond,
Yeah,
or
so yeah, we have carbon carbon double bond here. We have a carbon
so.
carbon double bond here. We have sp2.
So wouldn't that land somewhere like in the middle-ish,
These
right?
are all, 1, 2,
Or
3, 1, 2, 3, 1, 2, 3, 1, 2, 3.
or wait,
These are
no.
all sp2s.
Okay, wait, no, never mind. I take it back. No, then SP2 should be leftmost, right? Because
Yeah,
it's yeah,
let's see. Let's
it's
do A,
more stable than
B,
SP3.
C,
So
D.
that 30 80 is probably A.
Okay, so we'll put A here. And I don't know what the answer is. I just pulled this up. Okay. What
Okay.
about B?
Um, yeah, so B, yeah, okay, it's completely SP3. So let's put that at the 2961, 2929.
Okay, so we'll put B in this range.
And then yeah, and then I'm gonna assume that um mm, well, okay, I don't know if it's a 1827 or 1643, but I would say the next one is gonna be C because a triple bond is a stronger bond than double,
Wait,
right?
we're into, yes, yes, but we're also interpreting this wrong. This is we're supposed to be deciding, sorry, which which molecule this entire graph is
Oh,
representing. That was my bad. So, but to go with your point here, right, is we have all these sp3s here, right? We've got a little bit of sp2 here.
how do you
Okay.
know? Wait, how do you know that 3080 is SP2?
You're your graph. I mean, it tells you. That's why
Oh,
I'm saying,
oh.
like, you don't have to stress too much about some of this stuff because it literally tells you. You just have to get practice of like looking at these peaks and deciding, like looking at the numbers, deciding if, if you had this broad peak here that had this, like knowing that those two peaks mean that it's a first degree of mean, or knowing, whatever it is, knowing that at 1500 we don't look at anything, right? So
Mhm,
this, you can literally do this to your graph. And so really we're just looking at these. Let me erase some of this stuff. Let me erase this. So really you're just literally looking at this right here. Okay. So
mhm.
we're looking at this, which is an SP2,
Yeah.
this, which is SP3. And then if you look at your graph, what's around 1827?
I forget. 1827 is okay. I'm clearly not looking at the right graph.
No, you
Wait,
probably
sorry, where are
are.
you looking?
Um, so this.
There's nothing in the 18s.
Yeah. So you can kind of see here that there's this, roughly in this range, we might be looking at, either one of these, we're probably not going to see any of those, but we might see kind of,
It's likely going to be the double bond.
so yeah, and then what's that? And sometimes, again, sometimes like not every little thing matters, and you'll kind of pick up on that, right? So for now, let's just say we're not really sure about this, and that's
Wait,
fine.
so is it D? Is it describing D the whole
Yeah,
thing? Yeah,
yes.
because it has SP2 represented, SP3 has a double bond, which makes sense. But I don't know what
So what's 1643?
yeah, and that's not the double bond.
No, 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 it is, yeah.
Oh, it
Because
is. But
see,
then what's the 1827?
it's not, it's nothing. That's why I'm saying not everything. Here's your 1660 to 1600, right? So that
Oh,
would fall in this right here. So this is your carbon-carbon double bond, right?
yeah.
So we don't have any triple bonds, so we can get rid of that. We can't, well, we can get rid of both of these, but it's just by process of elimination because we both have SP2 and SP3, right? And so even just being able to do that, even if we weren't sure about anything else, we could say just by process of elimination that it was this one, right? Even if we
Mhm.
didn't know what this was, but we
Yeah.
knew for sure that we weren't going to have this and we weren't going to have this. And then a triple bond is going to be in the 2200s range, which is like, somewhere in here, and we have
Mhm.
nothing there. So then it
Yeah.
can't be the triple bond, right? So not every, see how all of these are like, not everything necessarily matters for your, for to be able to like read your graph.
Hmm. And then also just something else I just didn't understand too much is like when do you think to look for resonance and minor resonance contributors?
Yeah, I know, right? That's a good one. Um, so there is, let's see. Um, Something that she had said regarding, so the difference between like a ketone or aldehyde versus like a nitrogen group, nitrile group. Um, so it depends on what kind of um like what kind of like bond character it will have. Like if the bond character, like for a ketone, right? If we do this, do this, we end up getting this, right? Versus, which is perfectly fine, kind of. I mean, we don't really want a positive on a terminal, but whatever. But see, this has got single bond. This is a single bond here, so it's not really like, it's not going to want to be in this form. What I'm trying to say. Versus this. We need this. We need this to be correct. And then we've got this double bond. Whoops. What am I doing? I'm putting oxygens on here like this is electrons on here like this is an oxygen. Anyway, let's see. Do my little electrons here. Right, and so then this has like double bond character. So I would say that like if you don't like this isn't necessarily going, this would be like your minor resonance, right? Because it's not really, you've kind of created more, you've created your like formal charges,
Mm-hmm.
and it has your single bond versus this also you would consider this you would consider this because the minor resonance has a like a double bond character, so it's going to have higher frequencies.
Oh, okay. I see.
You see what I mean?
Uh-huh.
Like this you're not, it's not really changing, it's not really like affecting anything. Like this is going to have a higher frequency, a stronger bond than this already.
And also, oh, I was gonna say also maybe the fact that there's two charges makes it a little less
Yeah,
stable.
this one has two charges as well.
And then yeah. And then that yeah. Huh. Okay. But like on the spectroscopy graph, um,
Yes.
is
Like
there
this one or this one?
like either on page 10?
Oh yeah. Mm-hmm.
Um, what is the like distinguishing feature that tells you there's resonance or there is no feature? I just like wasn't making the
Let me
connection
see.
between the resonance and the graph.
Okay. So let's look at this. So amides have minor resonance contributors. Um, Let me see, where's the beginning of this? Even though the dipoles, okay. And then this is a conjugated system. Okay, so minor resonance contributors for conjugated aldehydes and ketones give the carbon double bond oxygen single bond character, yeah, which we just talked about. The more important the minor resonance contributors, the more single bond character it has, the weaker the carbon double bond oxygen, the lower the vibrational frequency. So higher vibrational frequency around 1680, sufficiently different from non-conjugated, which is 1710, to be reliable enough to distinguish this case. So your minor resonance, something that has a minor resonance is going to be lower because the bond versus in your minor resonance is more important, lower vibrational frequency. And that's the minor resonance. So have even more single bond character, the vibrational is less, thus decreased. Amides will have NH vibrations with peaks at 3300, which we've talked about before. More available, the minor contributor in the amide is even more important. So those amides also have minor resonance contributors In this case, the electrons involved in the resonance are non-bonding on nitrogen and thus more available. The minor contributor in the amide is even more important. So you're asking how we would know to look for that in the graph. Minor is a little bit.
Yeah, just like when do we have any indication that like resonance might be something that we should pay attention to?
Mm.
Probably not often. I don't know.
Yeah, I'm not like it's not really bringing a ton of stuff to mind, to be honest. Like, you know, I this was one of my stronger sections for sure, because it was very kind of straightforward. Um,
Yeah, I think like probably the examples that we're given are going to be a little bit straightforward. I don't know. I
have you
think that
guys?
I'm like getting into the weeds. I just like
Yeah.
I don't know. I just like to have like an intuition for things, and for this section, I just don't necessarily think I'm like the best at having an intuition. So,
Mm. Have you gotten your extra credit yet? Have you looked
like,
at it yet?
oh no, I haven't.
No, for this week. Because
Yeah, no, I didn't. I didn't do it yet.
I will I will say that her, yeah, like her extra credit is like, if you haven't figured that out yet, very indicative of what the exam is going to look like. And you really like, if you haven't looked at it yet, I'll just give you a little synopsis, basically how she's going to have you do it on this. And you could rewatch the office hours from earlier today too. You literally are going to label your major peaks of like what the wavelength is, what that corresponding bond type is, and the functional group. So, and you really just have to have some of that stuff, like, you know, I'm not going to say that that stuff might not be important, but there is some stuff that this gap notes and stuff is going to talk about that's not necessarily, it is more like you said, like getting into the weeds a little bit, and you're not going to have to like worry so much about some of that stuff. um if you just really familiarize yourself with this table on page 12, um you will do fine. I promise. If you know how to read this table, and you can't, when I filled it out, I put like alcohol or carboxylic acid or ketone or aldehyde, or right, and I started to do that on this thing right with you. But like, as long as you know, right, like this right here, right, like I started to write some of this stuff out. As long as you know what these things are, where they lie, right? That's why it's so important to know your functional groups, right? You'll
Mhm.
you'll do you'll do pretty good, because then when you see something, you'll make a graph, and you'll look at a graph and you'll write down your table. She does this for a reason, right? Where you have to identify, okay, this wavelength is here, this is the corresponding bond type, this is the corresponding functional group. And then once you have that table all laid out, if you see a molecule, you'll be able to say, oh, okay, there's this molecule has a triple bond and I have no triple bonds on my IR spectroscopy, like, you know so
Mhm.
it's a lot more simple and straightforward than some of these graphs. I do remember kind of going through these graphs and being like, oh my gosh, it was a lot, because there is a lot of like nuanced stuff, like with the resonance, with the, oh, this spike or that spike, or which exact area, or oh well, that spike I don't see anything, but it's still on there, and so um I would say go through. Do you do the extra credits? I don't know if you do, but
Yeah. Yeah, no, I,
yeah.
I always make sure I do it before the test.
Yeah, I highly recommend them, because it's pretty much, I mean, she
Yeah.
changes stuff a little bit, but it's basically like the test. So
Yeah.
it's very helpful to at least know what to expect. But you'll kind of see how it's not like this in the gap notes, which is why I think it probably feels a little more kind of overwhelming. but maybe even just reviewing when it comes to like these graphs, like reviewing how it is that she, and maybe just watch that portion of her office hours where she goes over it. I think it's page or I'm sorry, it's question number 6 onward, or I guess really is like 6. If you just watch her cover question number 6, you'll be able to see how she expects you to go through it and how you can kind of read those graphs, which is kind of like how I've been trying to explain it to you a little bit, is like, find the peak, like identify what the number is on like the peak. You won't necessarily have these numbers here, but you'll be able to generally tell, right? You can, if this is your three, like that's why I always drew those two lines. 1500, I think it is roughly, right? And is it 1500? I don't want to say, yeah, 1500 and 3000. And I already knew that like my SP2s were here, my SP3s were here, and then I could ignore everything on this side of it. So it left this very small kind of portion to read. And it
Mhm.
made things more bite-sized and palatable. And then when I would compare, because you get this graph, um, I'm gonna let me see. Oops, that's all I meant to do. But at the beginning of your exams, you have that. I'm sure you've seen it. Um, it doesn't say like SP2 or SP3 or anything like that, but it does have your graphs on there. So you'll be able to actually like see this. So you don't have to memorize these numbers. You just literally will compare it.
Yeah. Okay. I think I should need to just do some practice and it'll probably come easier.
Yeah, yeah. Just practice. Literally, just have this page with you. Have this
Mhm.
chart on page 12, wherever it is. Yep, page 12 in the spectroscopy. And look at this as you go through and just look at the different graphs. And just go on the practice site and just go through and practice um, and just write either tables or just go through and identify like, okay, these are the bonds that are in there, or these are the whatever it is that's in there, and then see if you can identify the molecule or however the question is presented. The more you practice it, and just remember, the homework site is level 1000 and the exams are like level 100, right? So if you can get through more than half of, like confidently, more than half the questions on the practice site, you're going to do just fine on the exam. So,
Mhm. Yeah.
yeah. And then, you've got this last part too is fun. When we get there, the de-shielding and all that. Those ones are pretty easy, I felt like, you know.
Yeah, I got through the majority of this content. I just have to do the last video, so whatever was at the end.
Yeah.
But I thought it was pretty okay.
Yeah, those ones aren't bad. So, and the honestly, reading the graphs, it really is not that bad either. Um, it's literally just going to be, when you do some practice stuff, you'll see. It's not going to be as bad as you're making it out to be right now. Right? It's always fear of the unknown. But yeah,
Yeah.
yeah.
No, no, for sure. Well, I will go practice and probably be back on Saturday as always.
All right, awesome. Well, I will be here. And if you've, got questions in the meantime, you're more than welcome to shoot me an email or a canvas and I'll answer them as best I can. So, but there's a lot of good stuff too. And sometimes on I didn't really use the ed discussion a lot um, when I was a student, but sometimes there can be some really good questions on there. So I've been trying to review them. Dr. Pillai is like quick on it. I told her I would help her to like answer the questions on there, but every single day that I check, she must get notifications like as they come up because I've only answered probably one question before her. She's very quick with it. So that's
Yeah,
another great
honestly,
resource.
I should use it. I've never actually used it, so I really, yeah. Well,
Yeah.
whatever.
Yeah, hop on. I mean, like it's a quick way to be able to like get her to answer because clearly she does it in like a millisecond. Um, God bless. But also you can see like other questions that maybe somebody else has the same question as you and it's already answered. So it is helpful. I don't know if you guys have a Discord. Sometimes those can kind of be give or take, right? Sometimes they're good and sometimes they're chaos. So,
Well,
but
yeah, just by the way, I know I told you kind of last time, but well, I don't know if you're like pre-med or what, but if you just change your mind, you should go into teaching because you're quite good at it.
oh, thank you so much. I do that's my dream retirement job, to teach at a university. So we'll see what happens. But I do enjoy teaching. I really do. It's definitely a passion of
Oh,
mine.
and you need to petition to do the second semester of Chem 2,
Okay.
please.
All right, well,
Just putting it
drop
out
a
there.
line. Yeah, I'll ask Dr. Pillai, who's teaching OChem too, and maybe put a bug in somebody's ear and say, hey, and I'd be happy to
No, I
accommodate
can
if it works
tell
out.
you who's teaching OChem too. It's
Oh,
on
who?
it's I have to like I'm logging into the thing to the my
Yeah,
ASU.
to your
I'll
yeah.
have it in 1 second. And
Are
just
you on
just you
are
know
you online or are you in person, but you're taking this like I solar, whatever it's called?
oh yeah, I'm like in person, but
Yeah,
I'm just taking this online.
yeah.
It's Needle Kova, Nedelkova.
Nedelkova. Let me see. I've never heard. Let me see.
Valentina.
Valentina, yeah.
Yeah.
There's no picture. Um, but yes, I see that she is teaching OChem too this summer.
So you got a
Interesting.
petition.
Yeah.
Petition for our sake, please.
Yeah. That is so funny. I wonder who this is. I've never heard of this person before. Although I'm not part of the School of Molecular Science. I'm part of um Seoul School of Life Sciences, but they're pretty kind of interconnected. So that's interesting. Well, I'll mention it, but you know, yeah.
Maybe I get lucky, maybe not. I don't know,
Yeah,
but
exactly.
you can always try.
Exactly. Well, when it comes to what's it called? The reviews, the class reviews, just put in a good word for me.
You know it. You'll get a glowing rating.
You were so funny. Oh my
Anyway,
goodness. Okay, Jackie. Well, listen, it's always a pleasure. I'm glad. Hopefully there was some things. I know we probably didn't answer all the questions to what you wanted, but yeah, don't make too hard of light work, So
no,
just
yeah.
get your
No,
graph,
yeah.
get your page 12 little table graph out and practice some problems. And just trust that it's really not going to be as bad as you think. So
Yeah. No, it'll be good.
yeah.
And I will be back Saturday. You know it. You can't get
Yeah.
rid of me. I'll be back again.
That's fine.
So
That's fine. That's like me. You're like a you're it's a me protege. I was the student who just never I never didn't show up to office hours.
yeah,
Uh,
well, that's me. So
yeah,
anyway.
it's a good way to get in, get opportunities and get into, and just always show your face, if you want. I don't know what is it that you want to do. I'm gonna stop
Um
recording so everybody doesn't have to listen to all this, but
yeah,